Imagine you're standing on a different world, not in a photograph, not on a screen, actually there, in a landscape that stretches red and cold and impossibly quiet in every direction. Your boot has pressed into the dust for the first time, leaving a mark that no wind will erase for centuries. Behind you is the lander that carried you down. In front of you, a landscape no human has ever walked. It looks like mission accomplished. And it is, but only just. That footprint proves someone arrived. What comes next? The 100 days that follow will prove something harder. Whether the place you've landed can keep you alive. The launch, the journey, the famous first step are the parts that make the headlines, and they deserve to. But the harder question, the one that actually decides the mission, comes after. By day 100, the question isn't whether humans can land on Mars. The landing already happened. The question is whether the landing has turned into something more. A place that can keep a crew alive without every morning becoming a recovery from the night before. Whether machines that left Earth years ago and have been sitting alone in one of the harshest environments in the solar system are still working well enough to trust with human lives. No official mission plan marks day 100 as a magic line, but it is a useful test window built from something real: surface operation studies, power system analysis, habitat engineering limits, and what planners have learned about how long it takes a crew to move from activation mode into genuine operational mode. 100 days is long enough to have survived the hardest part of the startup sequence. Long enough to surface the faults that only appear after weeks of real operation, and long enough to know whether the site is sustaining itself or slowly losing ground. We're going to walk through that test slowly, one problem at a time. Every engineering choice made years before launch, every piece of hardware sitting silently on the Martian surface, every decision about power and air and water and where to land, all of it comes to a reckoning in those first 100 days. 5 conditions have to be true at the same time, and by the end of tonight, you'll understand all 5, and why the first 100 days on Mars would decide everything. If you enjoy exploring questions like this with me, subscribing to the channel helps others find their way here too. Liking and sharing the video helps even more. Now, let's begin. Stay with the image for a moment. The engines have just cut. The dust is still settling. And before we do anything else, let's make a distinction that will shape everything that follows tonight. Picture the moment the engines cut. The crew runs through their checklist in the sudden silence. Hull integrity confirmed. Pressure holding. The power bus is stable. Life support reads nominal. They are on Mars. That is the landing. But it is not the base. This isn't just a question of words. It's a description of 2 completely different physical situations that look identical from the outside, but behave very differently under pressure. A landing means the vehicle and the crew survived. Entry, descent, touchdown, all of it worked. The lander is intact, pressurized, stocked with everything that left Earth. The crew is alive and able to function. That's what a successful landing delivers. A base means something more. It means the site around the crew can sustain them, not because the vehicle that brought them is still there, but because the infrastructure they need to survive is out there, working outside the ship. On Mars, the gap between those 2 things is the gap between alive for now and genuinely operational. Think of it this way. The lander is the most familiar environment on the planet. The crew knows its every interface. They've trained every failure mode for years. Its consumables were loaded with known quantities. Everything about it was tested before launch. It was the right vehicle for transport, but transport was its job. The mission wasn't designed to keep a crew alive inside a lander for months and then bring them home. It was designed to establish a surface presence, and a surface presence requires the systems outside the landing vehicle to work. Stepping outside into the base is a different proposition entirely. The habitat has been waiting through a Martian winter. The power system has been running in a low power state for months. The surface out there is accessible through an airlock the crew hasn't yet used in real Martian conditions. Pre-landed cargo is out there, somewhere, having survived the environment on its own. The question isn't whether they can land, they just did, The question is whether all of that hardware sitting out there has held together, come online correctly, and added up to something they can actually live in. 5 things have to be true at the same time, and all of them have to hold, before day 100 can mean what the mission needs it to mean. The first is a pre-built site, not bare ground, but a foundation that was already prepared. If it wasn't, the crew arrives at a starting point rather than a foundation. They spend the first weeks building systems from scratch, instead of activating systems that were designed to be ready. And the time cost of building from scratch, in a pressure suit, on a planet with extreme day-night temperature swings, drawing on consumables from a finite reserve, is not something you recover from by working harder. Everything else the mission was designed to accomplish gets compressed into whatever time remains after the delayed startup work is done. The second is a landing accurate enough to actually reach what was pre-positioned. If the landing missed the cargo by too much, the first EVA isn't an activation mission, it's a navigation problem. The crew has to assess whether the pre-positioned assets are within reach, what the terrain between them looks like at walking scale, and whether the vehicles can cover the gap without consuming margins the rest of the mission depends on. Every extra kilometer of separation is not just distance, it is EVA time, suit consumables, and vehicle battery capacity that the activation plan never accounted for. The third is continuous power, not mostly reliable power, but power that doesn't collapse during the Martian night or a dust event. If power is intermittent, no other system can find a stable state. When the power cycles up and down, the habitat management computers restart repeatedly. Logs get truncated, sensor baselines are lost, the trending data the crew uses to identify developing faults becomes incomplete. A habitat that has been through several power interruptions in its first week is a habitat whose condition is much harder to assess than one that has had continuous power from the moment of activation. The fourth is a habitat and life support system that run together as one machine, not as a collection of separate parts that merely share a pressurized room. If the habitat checkout reveals systems that are not functioning at specification together, life support running but the water loop marginal, thermal control adequate but oxygen generation slightly low, the crew has to decide what risks are acceptable versus what needs immediate remediation. Those decisions consume engineering judgment, crew time, and sometimes the consumables that the next decision point will depend on having available. And the fifth is crew time. By day 100, the daily schedule has to be moving toward planned work, the science, exploration, and sample collection the mission was funded to accomplish. If crew time cannot shift toward planned work, the base is still in its activation phase, past the point when activation was supposed to be complete. Every day the crew spends in activation mode is a day that the mission's productive goals are being deferred. If any one of those 5 is missing, the first 100 days are still the aftermath of a landing, not the beginning of a base. Here's the harder truth. Every one of those conditions was decided before the crew ever left Earth. The power system design, the habitat engineering, the cargo manifest, the landing accuracy hardware, the maintenance philosophy for life support. Those choices were locked in when the mission was planned. They either gave the crew a path to day 100 or they didn't. The crew's job on the surface is to find out which case is true and respond within the margins the architecture left them. Landing day doesn't create the base. It reveals whether the base was ready to be created. What happens in the next 100 days is the proof of which case is real. Now let the view widen. The crew's arrival on Mars is the second act, not the first. To understand why the first 100 days will go the way they go, you have to go back further, much further, to something that left Earth long before any human being committed to going. 26 months before the crew departs Earth, something leaves first. Not a scout mission, not a supply pod, the surface habitat itself. It lifts off and heads to Mars without a single person aboard, arriving and landing on its own, more than 2 years before the crew it was built to shelter. The Mars Ascent Vehicle follows. That's the ship the crew will one day use to leave Mars. It goes ahead too. Power equipment, exploration assets. All of it lands on Mars, while the crew is still on Earth, still training, still preparing. This isn't an unusual scheduling decision. It's a physical law of how missions to Mars work. Here's why. Cargo and crew have to travel on different paths. A cargo ship can take what's called a conjunction class transfer, a slow, fuel-efficient orbital route that burns far less propellant per kilogram of payload. Time doesn't matter to a crate of equipment. A year and a half in space is fine. For a crew, it's not fine. 6 months of weightlessness and radiation exposure is near the limit that mission planners can accept. The physiological consequences accumulate: cardiovascular changes, bone density effects, radiation dose building in tissue. A year and a half would be far too much. So the crew travels on a faster, more expensive path. But that path only opens during specific orbital windows when Earth and Mars align just right. The result is a gap of more than 2 years. The cargo goes on the earlier window, the crew follows later. By the time the crew launches, the habitat they're going to live in has already been standing on Mars for months. The power system has already been running. The fission reactor that will supply electrical power to the entire base landed during the pre-crew window. Its job in that period was to power the ISRU hardware, the equipment that produces oxygen from the Martian atmosphere, so that oxygen for the ascent vehicle's propellant could begin stockpiling before the crew ever committed to going. NASA's design reference architecture made this sequence explicit. Pre-crew deployment is not a logistical detail. It is the mission model, and here is the thought that changes everything. This is worth sitting with for a moment. The decision about whether this mission succeeds might already be settled before any human being commits to going. If the cargo landed well, if the habitat survived its first Martian winter, if the power came on and has been running, the crew is launching to a base that's waiting for them. They're committing to a place that machines have already proved is working at some level. If those things didn't happen, the crew isn't going to a base. They're going to an emergency. The crew departure authorization depends on whether the pre-crew phase has demonstrated sufficient site readiness. The crew launches knowing, within the limits of what telemetry can confirm, whether they're going to a prepared site or an emergency that arrived ahead of them. That knowledge changes how they plan the first weeks of surface operations, what contingencies they have ready, and what their margin for absorbing unexpected conditions looks like. What sufficient site readiness means concretely is a set of telemetry thresholds that mission planners define before the cargo ever launches. Power system uptime percentage, habitat pressure retention over a defined period, ascent vehicle propellant system integrity indicators, ISRU oxygen production confirmation. These are not aspirational targets. They are the conditions the mission architecture requires before it will commit the crew. An architecture that sends the crew regardless of whether those thresholds were met is an architecture that is relying on the crew to fix problems that should have been addressed by a follow-on robotic mission. And it is asking that crew to carry a risk that the entire system was designed to pre-screen. If the pre-crew telemetry does not meet those thresholds, the crew does not launch on that window. They wait for the next one. 26 months later, while an unmanned follow-up mission addresses the shortfall. That is a painful outcome. Years of delay, public attention exhausted, budget pressure intensified, but it is the option that the architecture built in, precisely because the alternative is worse. The most important period in the history of the first Mars base isn't the landing. It's the 26 months before it. Happening entirely without human hands in a place no one can reach, managed only by telemetry signals that take up to 20 minutes one way to arrive. That communication delay is worth pausing on. 20 minutes each way. No engineer can stand in front of the hardware. No technician can notice a developing problem with their hands. If a seal starts to fail or a connector develops a fault, the autonomous monitoring has to detect it, report it, and the Earth team has to develop a response and transmit it. Then wait another 20 minutes to see whether the response worked. Commanding a robotic manipulator to address a hardware problem across that delay is slow and uncertain. If the equipment was never designed for remote maintenance, the chance of solving anything complex is low. The architecture's answer to this limitation is to design the hardware to not need human intervention during the pre-crew window at all. That means components have to tolerate thermal cycling, dust, and radiation for the full duration. Telemetry has to show Earth-based engineers real system health, not just surface indicators, but the kind of trend data that reveals a developing problem before it becomes a failure. A Mars mission should not send people toward a site that is only hoped to be ready. It needs a readiness record from the surface: power telemetry, pressure readings, thermal behavior, oxygen production results, health data from the ascent vehicle. Those numbers become part of the go or no-go decision on Earth. If the surface systems cannot prove themselves while unattended, the crew should not be asked to prove them with their lives. Crew arrival isn't a founding moment in the way most people imagine. It's more like taking possession of an industrial site that has been running for 2 years, tended entirely by machines, waiting to see what kind of condition it's in. There is no second chance to deploy a habitat that depressurized during its first winter. There is no remote repair option for an ascent vehicle whose propellant system developed a fault the autonomous monitoring couldn't detect and report clearly. There is no emergency resupply for a power system that failed during the pre-crew window and took the ISRU hardware offline with it. These are not scenarios the crew can fix by working harder or improvising differently. They are conditions the crew inherits when they arrive, and those conditions define the mission's possible trajectory from the first day on the surface. The first Mars base may effectively succeed or fail before any human leaves Earth. Imagine a machine waiting alone. No crew inside, no technician walking over with a tool. Just hardware sitting in a landscape where the temperature swings more than 100 degrees every single day and no one is watching. That is the situation for over 2 years before the crew arrives. The habitat lander touches down. Pressurization sensors confirm the shell is holding. The power bus is live. Mission control marks cargo delivery successful. That's day 1 of the pre-crew window. The question for every day that follows, for more than 2 years of Martian weather, is whether intact on landing day still means usable on crew arrival day. Mars is a brutal storage environment. The temperature at mid-latitudes swings from well below minus 70 degrees Celsius before dawn to above zero by early afternoon. And that cycle, that full swing of more than 100 degrees, happens every single day, every 24 hours and 37 minutes, without pause, without mercy. Over a full Martian year, the pre-landed hardware goes through more than 600 of those cycles. Imagine the thermal stress of a refrigerator cycling to an oven and back 600 times, with no one to notice if something cracks or loosens. Every joint, every connector, every seal. Materials that were qualified in Earth thermal vacuum chambers were tested against specifications, but those specifications were developed from the best available models of Martian conditions, not from direct experience of the exact site the cargo landed on. The gap between the model and the place is where surprises live. And then there's the dust. Martian dust particles are just a few micrometers across, fine enough to work into gaps that look trivial during handling on Earth. Over months, they accumulate in connector interfaces. They drift into ventilation pathways. They settle on every external surface they can reach. On a solar panel, the effect is measurable and direct. Less light gets through, less power is generated. On a thermal rejection radiator, dust acts like insulation where you don't want insulation, forcing the system to work harder to shed the same amount of heat. On a sensor port, even a thin coating starts to alter the readings. The habitat has to manage all of this without a crew. Its own heating systems have to keep the interior within the temperature range its electronics require across hundreds of cold nights. Its thermal control has to function within whatever constrained power the pre-crew architecture can deliver, keeping the mechanical and electronic systems inside functional across hundreds of day-night cycles, with no ability to adjust based on real-time crew observation. The ascent vehicle presents its own specific concerns. It sits on the Mars surface in a fueled or partially fueled state, depending on what the ISRU system contributed during the pre-crew window. Its tanks sit under operating pressure. Its plumbing faces the same thermal cycling and dust environment as everything else on the surface. The ascent vehicle is the crew's only return path. A slow propellant leak is not a small problem. Neither is a valve that shows fatigue after hundreds of expansion cycles. A sensor drifting out of calibration can give the crew the wrong propellant reading, and the crew needs to find these faults before they depend on that vehicle with their lives. The surface vehicles have been sitting out there too, So have the geological instruments and the suit systems stored for later use. The exploration hardware is not fresh when the crew arrives. Battery packs in storage at Mars temperatures behave differently from battery packs in a temperature-controlled warehouse. Electronics that have been in a radiation environment for 2 years may have accumulated dose effects on their most sensitive components. Seals that were perfect when installed may have relaxed slightly under the repeated thermal cycle. None of this is guaranteed failure. The hardware was designed to survive exactly these conditions. Engineers ran lifetime models for each component, calculated from the best available knowledge of the Martian environment and from accelerated life testing on Earth. Those models set the spares manifests and the maintenance schedules the crew will work from. But models and reality always diverge, not always in dangerous ways, often in small ways that accumulate quietly. There is also the question of what survives storage inside the habitat itself. The cargo manifest includes biological and chemical stores that behave differently from mechanical components, medical supplies, certain food components, reagents for scientific instruments. These have shelf lives that were calculated against the storage temperature range the habitat was designed to maintain during the pre-crew window, not against the actual temperatures the habitat experienced during its first winter on Mars, which may or may not have stayed within the planned range continuously. Some pharmaceutical compounds degrade outside their temperature range. Degradation doesn't produce a warning light on a control panel. It simply reduces efficacy, sometimes in ways that are hard to detect without laboratory analysis that the first crew won't have access to. A medication that arrives at below its certified potency presents the crew with a difficult situation. They can conserve the remaining supply and hope the degradation was minor, or they can note the uncertainty in the medical log and apply conservative treatment margins that may affect how they manage crew health events for the rest of the mission. Food systems have a more forgiving degradation profile than medical supplies, but they are not immune to the pre-crew environment. Caloric density, micronutrient content, and palatability all change under temperature extremes and radiation exposure at rates that are hard to predict exactly. A crew that arrives to food stores that have degraded past their planned nutritional profile has a caloric and micronutrient management challenge on top of everything else in the startup phase. It's manageable, but it adds to the accounting that the crew and mission support have to maintain. There is also a quieter problem inside the survival window. The cargo isn't only waiting, it is aging. Lubricants thicken and separate under temperature cycling. Stored seals take compression set. Connectors that were clean at launch sit for months in a dusty, cold, low-pressure environment, then have to carry power or data the first time the crew asks them to. This is why the pre-crew period has to be treated as an operational test, not a parking interval. Telemetry from the habitat, ascent vehicle, power system, and surface equipment has to show more than simple survival. It has to show that the hardware still has margin. A system that is barely alive before the crew departs Earth is not waiting to become a base. It is waiting to become the first emergency. What the crew inherits on arrival day isn't fresh-off-the-truck equipment. It's machinery that has been through more than 2 years of one of the harshest environments in the solar system, without maintenance, with limited monitoring, and no ability to intervene when something starts going differently than planned. If the cargo held together, really held together, with margin, the crew has a foundation. If it didn't, the first 100 days begin as a recovery operation, and every hour spent on recovery is an hour not spent on the stabilization the mission needs. If you imagine the first Mars base as a flag planted at the most dramatic spot on the planet, a canyon rim, a volcanic peak, a polar ice field, the real map is less romantic. The site has to be chosen the way you'd choose a place where people must actually live and work for 18 months, not a place to photograph once. There is no perfect location for the first Mars base. That's not a pessimistic thought. It's just the truth of what it means to choose a place where several very different requirements all have to be satisfied at once, and those requirements don't naturally point toward the same spot on the map. So the site isn't chosen because it's the best for any one thing. It's chosen because it's good enough for all of them. Think of it like choosing where to build a home in an unfamiliar city. You want good schools, but the neighborhood with the best schools floods every spring. You want to be close to work, but close to work means a tiny lot. You want a big garden, but the houses with big gardens are an hour from everything else. Eventually you accept a place that's not ideal in any direction, but livable in all of them. That's site selection for Mars. And NASA's exploration zone planning work from 2015 and 2016 treated the problem as a systems trade rather than a geographic search. Not where on Mars is the most scientifically interesting terrain, but where on Mars can a mission satisfy a bundle of linked operational requirements all at the same time. No single criterion dominated. The zone had to satisfy all of them at a level that left each requirement within acceptable margins. The lander has to survive the ground it's aiming for. Human-rated vehicles need a surface that's flat, relatively clear, and at a low enough elevation that the thin Martian atmosphere provides useful deceleration during entry. Too many boulders, too much slope, terrain that gives the guidance system no room to maneuver. Any of those can rule out a site entirely. This single constraint can erase an otherwise compelling location from the map. The science may be strong, the water may be useful, but if the vehicle cannot safely arrive, the site doesn't exist for a crewed mission. The operating radius adds a spatial constraint on top of that. The crew needs to be able to reach terrain worth exploring, and then return from it. The exploration zone framework settled on roughly 100 kilometers as the practical human operating radius, the zone accessible by surface vehicle at realistic speeds with realistic battery capacities. 100 kilometers sounds generous until you think about what traversal on Mars actually means. Loose regolith, boulders to navigate around, slopes that add distance, overnight charging stops, route finding that adds kilometers to reach a target. That 100-kilometer circle on a map is really the outer edge of what's possible in ideal conditions, not the average of what the mission can expect. Water potential is perhaps the hardest constraint to satisfy. A viable base site needs access to water-rich feedstock, hydrogen-rich minerals or near-surface ice, in concentrations large enough to support ISRU extraction at useful rates. Trace water in mineral form spread across a wide area at low concentration doesn't meet this requirement. The ISRU hardware needed to extract and process water has mass limits and performance characteristics that constrain what kinds of deposits are actually usable. This requirement pushed candidate sites toward higher latitudes, where near-surface ice and hydrogen-rich minerals are more likely to occur in concentrations the equipment can work with. But higher latitudes on Mars come with their own set of trade-offs. Steeper thermal cycling across seasons, lower solar angles that reduce the contribution of any supplementary solar capacity, longer periods of reduced sunlight, more demanding dust storm seasons. A site at 60 degrees latitude may have excellent water potential and challenging everything else. Communications geometry adds a constraint that's easy to overlook. A base needs regular, reliable contact with Earth for operations planning, data transmission, and emergency communication. The geometry of Earth-Mars communications changes with their orbits. There are periods during every Mars orbit when direct radio contact is degraded or impossible because the Sun sits between the two planets. Orbital relay satellites can extend coverage, but the relay architecture available during an initial mission is limited. Some candidate sites also sit in the communications shadow of terrain features at certain times of day. A site that goes through regular blackouts during working hours carries operational risk that accumulates over the course of a mission. Power conditions interacted with the architecture choice in a specific way. Once NASA determined that nuclear fission would provide primary surface power for crewed Mars missions, the site selection pressure from solar conditions relaxed compared to what a solar primary architecture would have required. The fission reactor produces power regardless of latitude, season, or storm. But the supplementary and backup solar capacity that every architecture still carries for flexibility is still affected by solar angle and irradiance at the site. Higher latitude sites still see worse solar supplement performance, and that matters in the margins. Terrain safety and accessibility consistently cut against scientific interest. The most geologically compelling sites on Mars tend to be the most difficult to operate in. Canyon systems are scientifically rich. Volcanic fields are too. Polar regions and layered terrain can hold strong evidence. They are also difficult places to land, traverse, and maintain a habitat. A place that meets all of the safety and operational requirements is probably not the most visually dramatic corner of the Martian map. The exploration zone compromise produces a site that is scientifically interesting inside the operational envelope. Chosen, above all, because the mission can survive there and build towards something sustainable. Then there's the timing dimension. The site was chosen years before the mission launched, based on orbital imaging and computer models. The first weeks of crewed surface operations are the first time anyone actually confirms whether the orbital survey was accurate at the scale of a footstep, whether the terrain is really as traversable as the imaging suggested, whether the dust behaves like the models predicted, whether the ground beneath the habitat is as stable as it appeared from above, whether the near-surface material has the characteristics the resource models assumed. Those first weeks are when the planned mission meets the actual site. Usually, the differences are manageable adjustments, but the crew has to make them, and the answers change the traversal plans, cleaning schedules, maintenance assumptions, and resource projections for the rest of the mission. Now bring the view back to the sky. The crew isn't just trying to land on Mars. They're trying to land near the specific things that make staying alive possible. That distinction matters more than almost anything else in the descent, and it changes what the engineering has to do. The crew vehicle hits the top of the Martian atmosphere at somewhere between 5 and 7 kilometers per second. Pause on that for a moment. 5 kilometers every second, more than 3 miles per second. At that speed, the atmosphere isn't a pathway, it's a wall. Air molecules can't get out of the way fast enough, so they compress in front of the heat shield into a zone so hot, over 1000 degrees Celsius, that the shield itself has to burn to carry that heat away. The surface of the heat shield ablates, vaporizing and carrying energy away from the vehicle as it does. That's how entry works. Not by blocking the heat, by controlled self-destruction, shedding the shield material to protect what's behind it. This extreme deceleration phase bleeds off most of the velocity, but Mars's atmosphere is less than 1% as dense as Earth's at the surface, and it thins quickly with altitude. By the time a vehicle has slowed enough for parachutes to deploy effectively, it's already at relatively low altitude with significant velocity still to shed. The parachutes work in an environment with almost nothing to push against, generating a fraction of the drag force they would in Earth's atmosphere at the same deployment speed. The Raider rockets that fire for the final descent and touchdown have to do more of the remaining deceleration work than comparable Earth systems. Every robotic Mars lander in history used some version of this sequence: entry capsule, parachute, terminal descent. And in that history, 12 of 19 attempted Mars landings succeeded, 7 didn't. Those failures were spread across the operational history of Mars exploration. They didn't all happen in the early years before engineers understood the environment. Some involved guidance errors, some involved communication failures during descent, others involved mechanical problems. Some involved terrain that didn't match what the landing system expected. Each failure found the assumption that didn't survive contact with the actual environment. 7. A crewed mission can't accept odds anywhere near that rate. 7 failures out of 19 attempts is 37%. But the reliability problem, as hard as it is, isn't even the biggest challenge. For a crewed landing, there's an accuracy requirement that robotic missions never faced, and this is the more demanding difference. A robotic lander can miss its target by several kilometers and still complete a useful mission. Wherever the rover stops becomes its geology field site. The instruments work from wherever the vehicle ended up. The landing point is wherever the vehicle stopped. For a crew, that's not possible. The habitat is at a specific location. The ascent vehicle is at a specific location. The power system, the suit consumables, the spare parts, all of it is somewhere specific. The crew has to arrive at a position from which they can physically reach those assets, not eventually, in the first days, before their consumables have thinned and before they've had time to verify which systems are fully functional. Wind drift during entry is a factor that robotic missions could absorb and crewed missions cannot absorb at the same magnitude. Mars's atmospheric density varies with season, time of day, and global weather patterns. The same nominal entry trajectory can leave a vehicle at a different altitude with different remaining velocity, depending on conditions that day. That uncertainty propagates through every subsequent phase of descent. Managing it within the tighter accuracy margin required for a crewed cargo proximity landing requires active guidance and control throughout descent, not only during the early deceleration phase. And then there is the problem of the final descent itself. When retrorockets fire close to the Martian surface, they blast into the regolith below. Unconsolidated rock, dust, mineral aggregate, it ejects outward. At speed, a crew vehicle descending near the pre-landed habitat has to choreograph its approach so the plume never points at the habitat, the ascent vehicle, or any other surface asset the crew will need. Plume ejector can damage seals and coat optical surfaces with abrasive material. It can also destabilize structures that were designed to sit quietly on a stable surface, not to withstand particles hitting them at speed. Terrain hazard avoidance is the final specific challenge. Orbital imaging of Mars' surface features can currently resolve features down to roughly 1 meter in scale. That's enough to map boulders above a certain size and identify terrain features at the scale of the landing footprint. But it's not enough to guarantee a hazard-free touchdown zone in the specific patch of Mars where the crew vehicle will set down. A rock that is 40 centimeters tall, sitting in the nominal landing zone, will not appear in orbital imaging with sufficient confidence to be flagged as a hazard. Autonomous terrain relative navigation and dedicated hazard detection sensors on the vehicle improve the ability to identify and steer around hazards in real time. But they don't eliminate the risk. The consequence of a landing that misses the intended zone, or that damages the pre-positioned cargo through plume impingement or debris, is not a science setback. It is a base startup failure. The crew arrived expecting to occupy an industrial site that is now either too far away to use efficiently or partially broken by the arrival itself. And there's a timing problem inside the precision problem. The crew cannot spend the first week making long trips just to gather the pieces of the base. Every soul spent reaching the habitat, moving equipment, or confirming that cargo is close enough is a soul not spent bringing the base into stable operation. Distance converts into crew time, suit consumables, vehicle battery capacity, and risk. There is also a question of what the landing itself does to the terrain. The touchdown zone around the crew vehicle, the area of surface actually affected by engine plume during descent, has been physically altered. Regolith has been displaced and redistributed. Material that was sitting on the surface is now scattered across a broader area. If that area overlaps with cargo that was pre-positioned too close to the nominal landing zone, the interaction between plume ejector and pre-landed equipment becomes a real problem. Seals abraded, thermal coatings roughened, optical surfaces contaminated. Landing zone planning, therefore, has to include a geometric exclusion zone, a minimum separation between the intended touchdown point and any pre-positioned asset that accounts for the realistic spread of plume-driven debris at the vehicle's actual thrust level and descent angle. What makes this difficult is that the plume ejector distribution depends on the exact touchdown point which the landing system is trying to achieve but cannot guarantee within a perfect circle. The guidance system aims for a target. It may land within 100 meters. It may land at the edge of its accuracy envelope. The separation geometry that was adequate for a nominal landing may become marginal for a landing at the accuracy limit, if the cargo was positioned closer than the exclusion zone for the worst-case scenario. This geometry is a design constraint that works backward from the base layout, from where the habitat needs to be, where the power cable needs to route, and where the crew vehicle landing zone can be sited, to determine the exclusion distances and cargo placement that keeps all of them separated safely. A base layout that satisfies this constraint is one where even a landing at the edge of the accuracy envelope doesn't bring the plume over any pre-positioned surface asset. Landing accuracy isn't a technical metric in the abstract. It's an operational margin. A smaller miss distance means the crew starts with more time, more energy, and more options. A larger miss distance means the first 100 days begin by paying back a debt that was created in the final minutes of descent. Before we talk about air or water or habitat systems, listen for the simplest thing in the base, a steady hum, the sound of current moving through a cable buried in the Martian soil. Without it, every other promise about the base starts to fade. Everything on the surface of Mars runs on electricity. The atmosphere management system draws electrical current continuously, running the blowers that circulate air through the carbon dioxide removal hardware, powering the electrolysis unit that generates oxygen from water, driving the sensors that monitor atmospheric composition. The thermal control system draws current to run the pump loops that move heat away from the habitat interior and out to the external radiator panels. At night, It draws current to run the heaters that keep the habitat interior warm when the Martian surface outside drops below -70 Celsius. The communications system runs on electricity. Antennas, amplifiers, signal processors, and the computers that manage the uplink and downlink chain all draw from the power bus. A power interruption during an operations critical communication window with Earth isn't a minor inconvenience. For a crew that depends on timely instruction from mission control during a fault response, it's a serious problem. Surface vehicles run on battery packs that charge from the base power supply. Between traversals, vehicles are parked at charging stations that draw from the main power bus to restore battery capacity. The charging cycle is overnight for a typical traversal day. If the base power supply drops during the charging window, the vehicles don't complete their recharge, and the next traversal either starts with reduced range or doesn't start. Every maintenance tool in the habitat runs on electricity. Data loggers need it. Medical monitors need it. Scientific equipment needs it. The power bus is the substrate that all other base systems sit on top of. Lose the power bus and every other system begins a countdown toward failure. You might wonder, why not just use solar panels? They work everywhere. They're proven technology. Mars is in the inner solar system. The physics here is worth understanding. Mars receives only about 43% of the sunlight that Earth does, a direct consequence of the inverse square law and Mars's greater distance from the Sun. A solar panel that produces 1 kilowatt of power in Earth orbit produces roughly 430 watts at the equivalent Mars position. Before any other degradation factors are considered, the baseline solar resource at Mars is less than half what it is at Earth. Atmospheric transmission reduces it further. Even on a clear Martian day, the atmosphere scatters and absorbs some fraction of incoming sunlight. Dust in the atmosphere has a particularly strong effect, because the particle sizes responsible for most of the scattering are efficient at blocking the wavelengths that photovoltaic cells use most effectively. And then the dust settles on the panels directly. A solar panel installed on the Martian surface begins accumulating dust from its first day of operation. The accumulation is continuous, driven by the settling of atmospheric dust particles and by any wind movement that redistributes material across surfaces. A panel at full rated efficiency when deployed may be at 80% after several weeks. After several months, it may be at 60%. If a regional dust storm deposits heavy material that isn't cleaned, it may fall to 40% or below. The history of solar-powered Mars missions makes the operational consequence clear. Robotic missions powered by solar panels have been pushed into conservation or emergency mode by atmospheric events that are not unusual by Martian standards. The missions powered by nuclear decay operated through those same events without power disruption. We'll come back to those events later. For now, the point is this: the risk to a solar primary architecture on Mars isn't theoretical, it's documented. The decision NASA made for crewed missions is to use nuclear fission as the primary surface power source. A fission reactor generates electricity from controlled nuclear decay. It doesn't need sunlight. Dust doesn't affect its output. Night doesn't reduce it. Seasonal variation in solar angle doesn't apply. The design places the reactor about 1 kilometer from the habitat, far enough to keep the crew outside the highest dose zone from radiation produced during operation. Power travels from the reactor to the habitat through a buried distribution cable, protected underground from thermal cycling and UV exposure. Think about what that arrangement means. The base isn't a single point on the surface. It's a zone, a power source at one end, a cable running through the regolith, a habitat cluster at the other. The crew has to inspect the cable, monitor the power readings at both ends, and have procedures for cable faults. Managing that zone is part of the base's ongoing operational requirement. The current that flows through that cable is what makes everything real. Without it, the habitat is a sealed shell in an environment that will eventually overcome it. With it, the habitat breathes, it stays warm, it charges the vehicles, it runs the instruments. The site becomes infrastructure. Power budgeting is a daily operational discipline at the base, not just a planning exercise that happened before launch. The habitat's power management system tracks generation, storage state, and load simultaneously, prioritizing critical loads and shedding lower priority draws when the budget narrows. The crew has to understand that hierarchy intimately. If the reactor shows a health indicator that triggers a precautionary load reduction, The crew needs to know exactly what gets shed first, what stays on, and what the boundary is between sustainable reduced operations and a genuine emergency requiring different action. The communication system's place in that priority stack matters specifically because it is both a safety-critical system and a variable load. During a scheduled uplink window, communications hardware draws more than its standby power level. During an emergency requiring extended unplanned contact with Earth, it draws at peak load for longer than the normal window. In a situation where the crew is simultaneously managing a power reduction event and a developing system fault that they need to consult Earth on, both demands are at their highest at the same time. The architecture has to carry both without requiring the crew to choose between them. The crew also needs to know what the power system does when it's asked to change state. A system that looks stable under a constant load can still reveal problems when the habitat starts drawing more power during equipment checkout, water processing, airlock cycles, or vehicle charging. Those load changes are where weak connectors, poor thermal margins, and control software errors tend to appear first. So the first 100 days have to include more than steady operation. They have to include deliberate power exercises that confirm the full architecture performs under varying demand, not just the nominal steady state. A base survives by having more than one way through a bad day. Not endless backups, just enough extra paths that one failure doesn't become the whole story. This is what the word redundancy really means in an engineering context. Not perfection, not safety in the abstract. Time. The reactor is running, the cable is delivering power. That's the foundation. But a foundation alone isn't enough if one crack can bring everything down. A single reactor by itself has a sharp failure mode. If it has no storage, no backup generation, and no load management, then a reactor trip sends power to zero immediately. The cause could be a fault in the reactor control system, an anomaly in the cooling loop, a loss of communication between the reactor and the habitat's power management system. Any number of specific failure modes that a reactor operating in an uncontrolled environment can encounter. If the only thing standing between the crew and a power loss is the continued operation of one reactor, a single fault puts the crew in an immediate emergency with no second chance. So the architecture doesn't leave the base in that position. Storage sits between the reactor and the load. Battery banks that charge during normal operations when the reactor produces more than the instantaneous demand and take over the moment the reactor trips. The crew doesn't lose power. They lose a few hours. Enough to diagnose the fault. Enough to attempt a recovery procedure. Enough to make clear-headed decisions rather than panicked ones. Those hours are what the storage buys. Not comfort, not luxury. Time. How much time depends on the storage capacity and what's being sustained. The critical loads on the base, habitat life support, thermal control, and emergency communications, draw significantly less power than the full operational load that includes vehicle charging, instrument operation, and non-critical lighting. A storage system sized to sustain critical loads for several hours is different from a storage system sized to sustain full operational loads for the same period. The architecture defines which loads are critical and what the minimum continuity requirement is, and the crew has to know that boundary well before they need to enforce it under pressure. Supplementary solar panels add another layer of generation. Not as a primary source, the storm resilience and night cycle independence of the fission reactor is why it's primary, but as an efficiency improvement during good sunlight periods and additional charging current to the storage system when conditions allow. In a fission primary architecture, supplementary solar is a maintenance flexibility tool, not a life safety critical primary source. But those panels degrade. Dust accumulates on them at a continuous rate. A panel producing 500 watts at deployment may produce 350 watts 6 months later if it hasn't been cleaned. In a high dust period a year into the mission, it may be closer to 200 watts. Cleaning panels requires an EVA, crew time, suit consumables, and physical work outside. The scheduling of panel cleaning relative to other EVA priorities is part of the base operations planning the crew manages throughout the mission. Cold temperatures affect storage capacity. Battery chemistry has an operating temperature range, and below that range the available capacity drops. Martian nights can push ambient temperatures to -70 at mid-latitudes and colder at higher latitudes. The battery banks require active thermal management, heaters that keep them within their operating range during cold periods. Those heaters draw from the power they're protecting. The net power available from the storage system during a cold night is the stored energy minus the heating overhead. A storage system that is fully charged at sunset but imperfectly heated during the night may provide less net energy before sunrise than the nominal capacity suggests. How the crew experiences the first unplanned power event matters beyond the technical resolution. The event itself, a reactor trip, a distribution fault, a storage system that falls short of its expected discharge time, teaches the crew things about the actual behavior of their power architecture that no simulation provided. They learn exactly how the habitat's automated load-shedding sequence executes in real time. They learn whether the transition from primary generation to storage is smooth or produces a momentary voltage variation that causes any system to behave unexpectedly. They learn whether the emergency lighting comes on at the right threshold, and whether the habitat management system's automated fault responses are appropriate for the actual load profile the base is operating under. Every one of those observations goes into the fault log, and those log entries shape the written procedures the crew will follow the next time the power system requires manual intervention. Procedures that will be sharper, faster, and more specific to the actual hardware behavior than the procedures that launched with a mission from Earth. The distribution cable adds its own maintenance responsibility. The cable runs buried underground, but that's not perfect protection. Thermal cycling in the regolith moves the soil slightly over each Martian day-night cycle. The connectors at the cable ends are the highest risk points. Thermal cycling of connector interfaces is a known failure mode for ground-side power distribution equipment, and the Martian environment adds dust penetration as another stressor. The crew needs to inspect the cable connectors and monitor distribution system health at regular intervals. Panel cleaning, storage thermal management, cable inspection, and reactor health monitoring keep the backup layers usable. A power system that was redundant when it left Earth but hasn't been maintained in the first 100 days may have lost significant redundancy by the time a genuine fault occurs. The storage that was supposed to provide 4 hours of critical load coverage may only provide 2 if the batteries have been running cold. The supplementary panels that were supposed to provide backup generation may be operating at 40% of nominal output if they haven't been cleaned. Redundancy in a Mars base power architecture is a maintained state, not an installed condition. Day 100 is earned only when the base has survived a real power challenge, a reactor trip, a storm event, or a maintenance period that required the reactor to go offline for a scheduled inspection. It has to come through with the storage and backup systems performing as designed, not just in theory, in actual practice, with real numbers from real events. The crew has to test the backup, switch to it, measure how long it holds under the load they actually carry, know from direct experience what they have to work with before they truly need it. If a battery bank is meant to bridge 6 hours, the crew needs confidence from real charge and discharge data, not only from the qualification sheet that left Earth. That makes redundancy part of the daily operating culture of the base. Checked the way pressure is checked, logged the way filter life is logged. The question is not whether a backup exists. The question is whether the crew has proved it will work under the conditions they are actually living in. Now step inside. From the outside, the habitat already looks like shelter, a sealed, pressurized shell sitting on a planet that would kill you in minutes without it. But a sealed room and a working habitat are two completely different things. What has to happen between those two states is what the mission has to solve here. The surface habitat is on Mars. Its structure is intact. It's pressurized. From orbit, through a camera, it looks like shelter. It isn't yet, not in the way the mission needs. A pressurized shell is the beginning of a habitat. Between a sealed shell and a working outpost lies everything that runs inside the shell. The systems that process the atmosphere, manage heat, handle water, generate oxygen, and reject the warmth that builds up during the Martian day. NASA's habitation system development describes the surface habitat goal as self-sufficiency, a machine that, once fully deployed and checked out, can sustain crew life without external intervention for the duration of the stay. The gap between that specification and the operational reality is what the habitat checkout process closes. None of those systems were running at crew levels during the pre-crew window. Each one needs to be activated, checked out, calibrated and confirmed before the crew can trust their lives to it. Start with the air. Mars's atmosphere is 95% carbon dioxide. The crew breathes an oxygen-nitrogen mixture held at carefully controlled partial pressures. But as they breathe, they exhale carbon dioxide back into that same closed volume. Without removal, it builds up, first impairing cognitive function, then causing headache and disorientation, then becoming acutely dangerous. The scrubbing hardware, the chemical or mechanical system that removes carbon dioxide from the airstream, has to be running and confirmed operational before the crew spends extended time inside. This cannot wait for later in the checkout sequence. Oxygen generation is the second system that can't wait. The habitat carries stored oxygen for the initial period and contingency reserve, but the long-term life support model for a mission with no practical resupply depends on generating oxygen on site. Electrical current splits water molecules into hydrogen and oxygen. The oxygen is injected into the habitat atmosphere. The hydrogen is managed separately, stored, vented, or used in other systems depending on the architecture. The oxygen generation rate has to match the consumption rate to keep the partial pressure of oxygen in the habitat atmosphere stable. Keep that balance and the air stays breathable. Lose it and the margin toward danger begins to narrow. Water is woven through everything. Crew members exhale water vapor, lose it through perspiration, consume it for hydration and food. The habitat collects humidity from the air, processes it back to liquid, and recovers water from wastewater through multi-stage treatment to keep the total inventory in a closed loop. On a mission with no resupply, water recovery efficiency isn't a comfort metric, it's a survival one. Water that leaves the closed loop permanently, through an unrecovered leak, a treatment failure, a spill that can't be recollected, is water the crew doesn't have for the rest of the mission. Thermal control manages the extremes. During the Martian day, the habitat absorbs solar radiation and generates metabolic heat from the crew inside. At night, the outside drops to -70 or colder. The thermal control system actively rejects heat during the day using external radiator panels and actively warms the interior during the night. Those radiator panels are external surfaces sitting in the Martian environment, and dust accumulates on them. As it does, the panels become less efficient at radiating heat. Lower emissivity means less heat rejected per unit area. Less heat rejected means the thermal control system has to work harder, running longer cycles, drawing more power to maintain the same interior temperature. Over months without cleaning, the thermal management overhead of the habitat increases as the radiators degrade. Each of those systems arrived on Mars already stressed by the pre-crew window. They've been through hundreds of thermal cycles, accumulated dust, endured unattended operation for more than 2 years, and experienced radiation exposure that accumulates effects on sensitive electronics. The delivery mass constraints that forced minimum margins on every system mean each one arrived with less redundancy than an unconstrained design would have included. Every challenge present since the habitat landed, dust, thermal cycling, radiation, the demands of a low-power dormancy state, is still present now that the crew is inside. The crew's job during checkout isn't simply to flip switches, it's to confirm, system by system and reading by reading, that the habitat is behaving as designed in the actual Martian environment, not in the Earth thermal vacuum chambers where it was qualified, not in the simulations where the analytical models were validated. Here, at this specific site, under the actual dust, thermal and radiation environment of this Martian location, the habitat becomes a working outpost when all of those systems are running simultaneously within their specifications, and the crew has accumulated enough data to know what normal looks like. That baseline, what carbon dioxide levels normally read at this crew size and activity level, what the water loop flow rate normally is at this operating temperature, what the power draw from the atmosphere management system normally amounts to across a full Martian day-night cycle, is what makes the difference between a sensor drifting and a system failing. Without a baseline, those two things look identical. With it, the crew can see a developing fault before it becomes a crisis. Building that baseline takes time and requires the systems to be stable enough to produce repeatable readings over multiple measurement cycles. A habitat that is still in active checkout, systems being brought online one by one, calibrated, adjusted, verified, is not yet producing a reliable baseline. Each new system brought online changes the overall load on the power bus, adds a new heat source, and adds new consumers of atmosphere and water resources. The habitat's steady-state condition only becomes visible when all systems are running simultaneously and have settled into their normal operating ranges. That settling period takes at minimum several Martian days, and longer if any system requires adjustment after initial activation, or if the interaction between two systems produces an unexpected result that has to be investigated. This is one of the reasons the checkout phase is front-loaded in the mission plan. The sooner the systems are all running and settling, the sooner the baseline becomes available. The sooner the baseline is available, the sooner the crew can interpret their daily monitoring as operational information rather than activation data. And the sooner they have real operational information, the sooner they can make reliable decisions about what the habitat needs in the weeks ahead. This is where the story becomes less cinematic and more human. Breathing on Mars is not a single achievement, not a moment that happens once and is then secured. It is something that has to keep being done every day, by systems that wear out, and by a crew that has to keep them working with whatever they brought. We have a good reference point for what this actually looks like. The International Space Station has been continuously occupied since November 2000. In the years since, its life support systems have required continuous maintenance. Pump impellers wear and require replacement. Separator membranes in the water processing system degrade and require servicing. The urine processor assembly, which recovers water from crew urine as part of the station's closed water loop, has accumulated a maintenance history that the original design documentation could not have fully anticipated. The carbon dioxide removal systems cycle through their beds at rates that match the design requirements. But the beds themselves and the associated plumbing and valves accumulate wear that requires attention. This is not evidence of poor engineering. It is what life support systems do under continuous crewed operation. They are complex assemblies of mechanical components, chemical media, and active electronics in an environment that is unforgiving of failures, and that has no margin for the kind of routine wear acceptance that industrial systems on Earth manage, with easy access to parts and technicians. Now here is the critical difference between maintaining life support on the International Space Station and maintaining it on Mars. On ISS, when a component fails beyond the crew's ability to repair using available materials, a cargo vehicle arrives within months. Logistics flights from multiple providers carry spare parts, replacement chemical beds, new membrane modules, and whatever else the maintenance manifest requires. The turnaround from an identified component need to a delivered replacement is measured in weeks to months at most. If a particularly critical spare runs short, there is a defined supply chain and a response timeline that can be accelerated. On Mars, there is no resupply. The trip from Earth to Mars at minimum energy transfer takes roughly 7 months for cargo. The orbital window for that trip opens only once every 26 months. If the crew is in their 9th month on the surface and a critical life support spare runs out, the next possible resupply cannot arrive for another 18 months at the earliest, and only if a resupply mission was already being prepared before the crew ever launched. The design response to this constraint is a different philosophy for how life support hardware should be built and operated on Mars. Not maximum performance, maximum probability of continued operation through the entire mission duration, and alongside that, maintainability. Components the crew can service using the tools and skills they have, and a sparing philosophy that accounts for the consequences of running out, not only the probability of failure. The maintenance workbench in the first Mars habitat reflects these priorities. Filter cartridges for the carbon dioxide removal system, supplied in quantities calculated from the expected replacement rate plus a safety margin. Membrane modules for the water recovery system, sized to last the mission with margin. Seals for the airlock mechanism, supplied in numbers that account for both scheduled replacement and unscheduled failures from the thermal cycling the mechanism experiences on every EVA cycle. Spare electronics for the sensors and controllers that monitor and regulate the most critical parameters. Each of those quantities was determined by the mass budget, the expected service life, and a calculated failure rate. Each represents a bet that the component will last as long as qualification testing suggested, and that the crew won't encounter a failure mode that requires more replacements than the manifest allocated. Some of those bets will be wrong. Components will fail sooner than predicted. New failure modes will appear that weren't anticipated. A component allocated at 12 units for an 18-month stay might actually need 15. These deviations aren't signs of failure, they're the normal information that emerges when hardware meets a real environment for the first time. The spares management problem is compounded by the fact that some components have dual-use potential. A seal intended for one system may be adaptable to another if the original application has failed and the spare stock is exhausted. A filter material designed for one fluid application may work in another with modifications the crew can perform. This kind of cross-system resource management, improvising solutions within the available materials on the surface, is a real capability that Mars mission crews will need to develop. The supply chain that keeps ISS crews in properly specified spare parts doesn't exist for Mars. What exists is what was launched. And there's an information dimension to the problem that comes before the hardware dimension. When a spare starts running low, the crew needs to know how many replacements remain, what the current consumption rate projects as the end of supply point, whether that point falls before or after the end of the surface stay, and what options exist for extending the supply if needed. On a Mars mission, that calculation has to come from what is on the surface. There is no other source. Tracking usage, projecting consumption, identifying cross-use candidates from other system manifests, and performing conservation repairs that extend component life. These are life support functions with no real equivalent in the history of previous human spaceflight. The first 30 days of life support operation produce the most important dataset the crew will have for managing the rest of the mission. Actual consumption rates versus planned. Every consumable has a planned consumption rate that was calculated from crew size, activity level, system efficiency assumptions, and operational tempo estimates. Those numbers were derived from the best available data before launch: ISS operational experience, terrestrial analog testing, manufacturer specifications, and engineering models. But the actual consumption rate on Mars, at this specific crew activity level, with these specific hardware units, in this specific operational environment, may differ from every one of those inputs. If the oxygen generation system is producing slightly less than the consumption rate during high-activity EVA periods, the crew needs to know that within the first 2 weeks, not the first 2 months. If the water recovery loop is returning slightly less water per cycle than the efficiency model predicted, adjusting water usage behavior early protects the reserve for the second half of the mission. Every day of accurate consumption data that the crew has before the first inventory checkpoint is a day of increased confidence in the resource projection for the rest of the stay. What keeps the life support stack functional across an unresupplied mission is the crew's ability to identify a developing fault early, isolate it to the smallest affected subsystem, repair or replace the relevant component using what they have, and where the right component isn't available, adapt, finding another component in inventory that can serve a similar function, improvising a repair from available materials, operating the system in a degraded mode that extends remaining service life, accepting a reduced capability until the mission ends. A camp is what you get when maintenance is the dominant activity, when the crew's time is consumed keeping the life support equipment barely alive. An outpost is what you get when maintenance is heavy but scheduled, time-consuming, skill-intensive, controlled by steady checks, but not so consuming that the planned mission work disappears. Day 100 needs that second condition. You may have heard the phrase, living off the land. On Mars, that idea is genuinely powerful. It's also easy to misunderstand, and getting it wrong matters for the first 100 days in a very specific way. Start with what's actually out there, on the other side of the habitat wall. The Martian atmosphere is 95% carbon dioxide, one carbon atom bonded to 2 oxygen atoms, and that molecule is everywhere, at every location, every elevation, every time of day. There is enough of it across the entire surface of Mars that any device capable of pulling oxygen atoms out of it has an effectively unlimited feedstock. That's the tempting part. If a machine can do that, extract breathable oxygen from carbon dioxide, then Mars stops being purely a place that consumes supplies. It becomes a place that gives something back. The question has always been practical. Can such a machine actually work, alone on another planet, far from the engineers who built it, with no hands-on help when something goes wrong? We now have a first answer. The Perseverance rover landed in 2021, carrying a small experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. Picture a box roughly the size of a car battery. MOXIE heats a ceramic element to around 800 degrees Celsius, passes carbon dioxide across it, and uses electricity to strip oxygen ions from the molecules. Those ions recombine on the far side as pure molecular oxygen, the same gas that makes up 21% of Earth's air. It worked. On Mars, in the actual Martian atmosphere, not a simulation. Across 16 separate test runs during the Perseverance mission, MOXIE produced a total of 122 grams of oxygen. Its best single run reached 12 grams per hour. Pause on that number for a moment. 122 grams is a beautiful scientific result. It is not a human supply system. A crew member working hard in a pressure suit uses roughly 1 kilogram of oxygen per hour. That's about 8 times MOXIE's best hourly output. A crew of 5, accounting for breathing, EVA use, and contingency reserves, needs several kilograms every day. MOXIE proved the door exists. It did not build the house behind the door. So why does ISRU still matter so much to the mission? Think of it as a second account rather than the wallet in your pocket. Oxygen is among the heaviest things a Mars mission needs to carry. The oxygen required for the ascent vehicle's propellant alone weighs many tons. If that oxygen can be produced on Mars, before the crew ever departs Earth, during the pre-crew window when the ISRU hardware runs unattended, then the cargo ship that launched 2 years earlier doesn't need to carry it. That frees up mass for food, spare parts, backup hardware, scientific instruments, things that make the difference between a mission that survives and one that thrives. Pre-crew ISRU that works changes the entire cargo architecture of the mission. The same logic extends to water. Candidate base sites were evaluated on whether the ground beneath them contained water-rich minerals or near-surface ice, in concentrations the ISRU hardware could actually extract at useful rates. Not trace amounts spread thinly across a wide area, but deposits concentrated enough to feed processing equipment at a meaningful rate. If water can be produced locally, it adds to life support reserves, provides radiation shielding material, and reduces what the next launch window has to carry. But, and this is the distinction the first 100 days hinge on, a buffer is not the same as a rescue. The ISRU hardware has been sitting outside, unattended, for more than 2 years. Dust, thermal cycling, radiation, whatever faults developed during the pre-crew window, the system carries them into crew arrival day. Those first weeks on the surface are not the moment to discover that the base needs the ISRU system running at full performance just to keep the air breathable. The pre-landed consumables, the oxygen, food, and water that came with the cargo, are what the crew depends on for daily survival in the first weeks. The ISRU system's role in the first 100 days is to get back to full health under human care, clean the filters, diagnose what the pre-crew window changed, confirm it can run reliably under supervision before trusting it with a larger share of the supply picture. If you imagine the crew watching the oxygen numbers come in during those early tests, don't picture celebration first. Picture careful attention. The output rises. They record it. The temperature holds steady. They record that too. A valve responds cleanly. A filter shows less contamination than expected, or more. Each small reading turns a promise into a known behavior. That is how a resource system earns trust. Not through one dramatic result, but through a quiet chain of repeatable ones. What those 100 days produce is something no Earth test could. Operational knowledge of how this specific equipment performs at this specific site under Mars conditions with human maintenance. That knowledge is the design input for the next mission's hardware. It shapes the cargo manifest for the next launch window. It determines how much of the resource burden the second mission can safely shift onto the ground. The crew who operate the ISRU system in the first 100 days are, in a real sense, performing the qualification test that makes a permanent Mars presence eventually possible, even if the oxygen numbers from those early runs are modest. A small number can still be a large piece of knowledge. The goal for day 100 is not for ISRU to be saving the crew. In a well-designed mission, it shouldn't have to. The goal is for the crew to have proved where the next margin can come from, and to have turned one piece of Mars from scenery into supply. After landing, every instinct says, begin, drive out, collect samples, prove the mission is alive. The surface is right there, a few meters past the airlock. Years of training have been leading to exactly this moment, but the first week on Mars asks for something quieter. And understanding why is one of the most counterintuitive things about how a Mars base actually starts. The crew is on Mars. The checklist is complete. Inside the habitat, pressure is stable. Life support reads nominal. The airlock is cycling correctly. Through the viewport, the surface of Mars is visible as a physical environment for the first time. Not a camera image, not a simulation, but an actual landscape a few meters away. The first step onto that surface happens on Sol 4. Not Sol 1, not Sol 2, Sol 4. NASA's 30 Sol surface reference mission is the most detailed published operational plan for the opening period of a crewed Mars surface stay. It describes the first sols with specific assignments, and those assignments reflect what has to happen before the crew can work effectively on the surface. Not what the crew wants to do, but what the mission needs them to do first. Sols 1, 2, and 3 belong to crew acclimation. The crew has just completed a transit of several months in microgravity. Their bodies adapted to weightlessness during the flight. Cardiovascular responses changed, fluid shifted toward the upper body, skeletal loading patterns adjusted. Readaptation to gravity begins on landing day, but it doesn't complete instantly. The vestibular system, which manages balance and spatial orientation, has to recalibrate to an environment where up and down are consistent again. Coordination returns, but early on it requires active attention. A step that would be automatic on Earth requires a conscious decision in the first days on Mars. And they've never been in Martian gravity before. 38% of Earth's gravitational pull, not zero gravity, not Earth gravity. Something in between that no training environment could replicate for sustained periods. Parabolic flights in Earth aircraft produce seconds of reduced gravity. An orbital station is weightless. The training done in normal gravity and in microgravity parabolas did not provide experience in sustained 38% gravity with a surface suit on. There is no way to train for that except by actually being in it. So the first 3 sols are cardiovascular checks at rest and under mild exertion, coordination assessments that reveal how well balance and motor control have adapted, medical monitoring that catches any crew member whose adaptation is slower than expected. These aren't bureaucratic requirements. They're the data that determines whether each crew member is ready to put on a pressure suit, cycle through an airlock into an atmosphere with no oxygen, and perform physical work at a level of risk that has no equivalent anywhere on Earth. Only then should they exit into an environment where a single suit failure is a life-threatening event. Sol 4 is the first EVA, and it's not exploration. The pressure suit system is confirmed operational under actual Martian surface conditions for the first time. The airlock cycle, depressurization, equalization with the external environment, exterior door operation, re-entry, repressurization, is confirmed to work correctly with a suited crew member executing it in Martian gravity. The mobility hardware is checked. Gloves allow the grip precision the crew trained for. The boot interface with the Martian surface is assessed. Joint mobility is within the operational range the suit design intended. The crew spends time on the surface of Mars for the first time on Sol 4. They note how the suit feels under actual conditions. They observe the terrain immediately outside the airlock, which their training prepared them for conceptually, but not experientially. They build direct physical knowledge of the environment they will be working in for the rest of the surface stay. Sol 5 is cargo offload, the physical work of moving equipment from wherever it arrived to the positions the crew will work from. Heavy items are carried or repositioned. The path between the habitat airlock and the cargo positions is confirmed for accessibility in a pressure suit with limited mobility. The inventory of what arrived is physically confirmed against the manifest, with the crew noting the condition of anything that shows external damage or unexpected surface contamination. This sequence isn't timidity. It's the application of lessons from every human spaceflight program about what happens when crews enter unfamiliar operational environments. For this crew, this is a surface they have never been on. Their training was based on simulations, analog environments, and extrapolation from robotic mission data. Those first EVA days are when the assumptions meet the physical reality of this specific site. The terrain may be more uneven than imaging suggested, The dust underfoot may behave differently than training surfaces. The slope between the habitat and the cargo offload position may require a different walking technique than the baseline training anticipated. Every one of those calibrations is information the crew needs before the pace increases. A crew that begins high-intensity EVA operations on Sol 2 is building their operational rhythm on a foundation they haven't verified yet. A disoriented first EVA can produce an injury, a suit emergency, or a navigation error. Exactly the early mission crises the first week restraint protocol is designed to prevent. The restraint is hard, the surface is there, the science targets are visible. The crew has trained for years for this, but the base is still new to itself, and every system is producing its first real data with people inside the loop. That data protects the mission more than an early traverse does. The first week also sets the culture. If the crew accepts vague status readings early, those readings become normal. If they insist on specific numbers, clear inspection records, and clean handoffs between shifts, the base begins with a different kind of discipline. Mars rewards the specific habit. A pressure value written down today can explain a leak trend 3 weeks from now. A photograph of a cable connector on Sol 2 can show whether dust or thermal cycling changed it by Sol 30. Mission control cannot smell dust in the airlock or feel a latch resist by hand. The crew has to translate those small physical clues into records that can survive the communication delay. The better those early records are, the less the mission depends on guesswork when the same system behaves differently later. Restraint is how the base earns trust before it spends it. The base earns that trust by becoming legible before it becomes ambitious. And that patience, one reading, one inspection, one confirmed measurement at a time, is part of the engineering. It is also a real survival margin. And that margin has to be earned slowly before the mission spends it. By the second and third week, Mars starts answering back. Not with one big disaster, with small mismatches between the plan and the place, slight differences that add up to something important if you're paying attention, and to something dangerous if you're not. Between Sol 10 and Sol 30, the character of the work changes. The urgent early scramble of landing and initial checkout gives way to something more deliberate, systematic fault-finding, and the slow building of real operational knowledge from hardware that has now been running for weeks in the actual Martian environment. The power system has completed 10 full day-night cycles under habitat load. The surface vehicles have been on their first traversals. The suits have been through multiple EVA cycles. The life support stack has been running continuously with the crew inside. Each of those systems has produced data that didn't exist before crew arrival. Now that data is available, and it tells the crew which systems are performing within expected ranges and which ones aren't. The first Sol 10 inspection cycle begins to reveal the patterns. The carbon dioxide removal filter is showing degradation indicators slightly earlier than the specification predicted. It was qualified for 90 days under Earth test conditions. The first 10 Martian days of real operation suggest the replacement interval may be shorter. This isn't a crisis. There are enough cartridges in the manifest to handle some shortening, but the consumption rate assumption has to change. The remaining supply calculation has to change. Mission planning has to incorporate this. The thermal rejection panels on the habitat exterior are reading slightly low. Dust accumulated during the pre-crew window was never cleaned. The emissivity has dropped by a measurable fraction. The thermal control system is compensating by running its pump loop at higher flow rates, drawing slightly more power. Not a crisis, but an entry on the maintenance schedule, a cleaning EVA within the next 10 sols. One surface vehicle returned from its first real traversal with a slightly different battery capacity reading than its qualification baseline. Real Mars gravity, real temperatures, real terrain that required more motor current than the average terrain model assumed. The traversal planning model for that vehicle gets updated with measured values that replace the pre-mission estimates. The charging cycle numbers from the first month are another critical dataset. How long does each vehicle take to recover full charge after a standard traversal? What is the actual available capacity when a vehicle returns from a full-range EVA? Does the charging rate change when ambient temperature is lower? Those numbers, confirmed across multiple traversal cycles in the first month, give the crew the EVA planning data they need for the rest of the mission. Modeled estimates arrived with the crew. Measured values at this site under these conditions replace them. Communications control settles into a rhythm too. The uplink and downlink schedule finds its pattern. The crew learns which information to package at which point in the Martian day for optimal transmission windows. System status data is high enough priority to include in every uplink. Anomaly reports need a format the mission control team on Earth can understand quickly, despite the communication delay. The first Sol 10 inspection also produces the first real traversal map. Not the orbital imaging the mission launched with, but ground truth observations made at walking scale by the crew who will use those routes for the next 18 months. Rocks that orbital imaging placed at the edge of the landing footprint turn out to be larger than estimated. A slope between the habitat and the cargo array is steeper than the terrain model suggested. A stretch of surface that appeared clear from orbit has angular debris that makes vehicle navigation at speed inadvisable. Each of these observations updates the traverse plan for the rest of the mission, adjusting the routes, the average speeds, the battery consumption models, the daily turnaround times. These updates are not failures of planning. They are the mission plan functioning as designed, pre-mission estimates replaced by actual surface measurements, made by the people who have to live within them for the rest of the stay. By Sol 30, the crew should be able to answer the operating question that controls the next phase. Is the base getting easier to manage or harder? Not easier in the sense that problems have disappeared. Easier in the sense that the crew's response to problems is getting faster because the hardware is becoming familiar. Tasks that required extended problem solving on Sol 5 are taking less time on Sol 25. The maintenance board shows upcoming intervals that are predictable rather than surprising. The fault log has more closed entries than open ones. If that's the condition at Sol 30, day 100 is accessible. The trajectory is toward an operation. If the fault log is growing faster than its closing, if the same task that took 4 hours in week 1 still takes 4 hours in week 4, if unplanned maintenance is consistently crowding out planned maintenance, the base has a structural problem that more effort alone won't resolve. There's a subtler version of this problem that's easy to miss. A base whose fault log is stable but whose unplanned maintenance is consistently displacing planned maintenance is building a debt that eventually collects. Planned maintenance keeps hardware in the condition the mission assumed. Every deferred service interval moves the hardware slightly further from its nominal state. Enough deferrals and the hardware starts generating faults at rates above planned, which creates more unplanned maintenance, which creates more deferrals. The cycle reinforces itself. If the crew can execute planned maintenance at the rate the schedule requires, and also respond to unplanned findings without falling behind, the base is moving in the right direction. If planned maintenance is being consistently deferred because unplanned maintenance is consuming the available time, the base is in a trajectory that leads to more failures, not fewer. The work between Sol 10 and Sol 30, methodical execution of the maintenance schedule while systematically closing the fault log from the first week, is some of the most important operational work of the entire mission. Not the most visible, not the most dramatic, but the most foundational. There's also the matter of the crew's own physiological adaptation to this point in the mission. By Sol 30, the acute effects of the transit have cleared for most crew members. The vestibular recalibration that made the first EVAs require careful attention is largely complete. Cardiovascular function has mostly readapted to gravity. The crew can perform EVA work at something close to the sustained output their training prepared them for. But Mars-specific adaptation continues past Sol 30. The suit systems, the terrain, the physical demands of working in reduced gravity with a pressurized garment, the perceptual adjustments to an environment where everything looks slightly different from Earth training sites. The crew is still building those physical habits in the first month, and they're doing it while managing a fault log, executing maintenance, and communicating operational status to Earth across a delay that makes quick back-and-forth questions impossible. The cumulative cognitive load of those first 30 sols is one of the least modeled aspects of early Mars surface operations. Crew members adapt, but they adapt differently and at different rates. Understanding how each person on the team is carrying that load and redistributing task assignments as individual capacity varies is part of what the mission commander manages across the first month, alongside the technical fault log that everyone can see clearly. The answer to whether day 100 is achievable is already forming in the maintenance data of the first month. One good day can fool you. Even one good week can fool you. A base becomes real only when it can repeat its own success, when the things that worked the first time still work the second time, under the same conditions and the same load. Between day 30 and day 100, a different kind of question takes over. The first month asked, can the crew stay alive? Can the systems hold together? Can the habitat maintain the conditions the crew needs? By day 30, if power has been continuous and the habitat is pressurized and the life support stack is functional, those questions have a provisional yes. The systems have been through a month of real Martian conditions. Known faults have been identified and managed. The crew is operational. Now the question is something harder. Can the site keep functioning through a complete operational cycle, high-tempo fieldwork, then low-tempo recovery, and emerge from the other side ready to do it again? An outpost isn't a site that survived one demanding period. It's a site that can survive the cycle repeatedly. NASA's longer surface operations work modeled this explicitly. The mission rhythm alternates between two modes. One is higher tempo, traverse and fieldwork, vehicles going out, samples being collected, geological surveys running, science instruments operating. The other is lower tempo, recovery, restocking, recharging, maintenance, repair, crew recuperation. The lower tempo period is not dead time. It is the operational foundation that the next higher tempo period depends on. Picture what that cycle looks like in practice. Several weeks of intensive traversal and fieldwork, then a recovery period. The recovery period has to restore the base to operational readiness. Vehicles recharged and inspected, suits serviced, consumables restocked from reserves, maintenance completed, crew ready. If the recovery period achieves all of that, the site can begin another intensive period from roughly the same starting position as the first. A site can do 3 weeks of intensive work and still fail the larger test. If the recovery period doesn't fully restore what the work period consumed, batteries back to operational charge, maintenance tasks complete, reserves at planned levels, the next cycle begins from a weaker position, and the cycle after that from a weaker position still. Eventually the margin runs out. The maintenance board tells this story plainly. Service intervals that were executed on time, open anomaly items with clear assessments of how each one affects the next cycle, upcoming work that's scheduled rather than discovered as a surprise. A board that's mostly clean says the base is running from a position of forward planning. A board with deferred service intervals from last week says the base is falling behind its own requirements. Deferred maintenance accumulates exactly the way you'd expect. A filter replacement deferred by 5 sols consumes those 5 sols of remaining service life. Deferred by 10, then 15. The filter moves past its service interval, system performance begins to degrade, a new finding goes into the fault log, and now there's more maintenance load on the crew, making it harder to catch up. A working restock, recharge, repair cycle has a plain look when it's functioning. Vehicle batteries are at their operational starting capacity at the beginning of each work period. Suit consumables are at their planned starting levels. Consumable reserves for oxygen, water, and food are at the levels the mission plan predicted for this point, adjusted for actual consumption rates from the first month. For the next traverse, the crew is using actual known good vehicle performance data rather than pre-mission estimates. Day 100 is the first point at which the evidence of real repeatability can be assessed, not one cycle. 2. With comparison data showing whether the second cycle started in a comparable or worse position than the first. If the second cycle begins in roughly the same operational state as the first, the cycle works. The maintenance work during the recovery period was sufficient to restore the base to operational readiness. The site can sustain operations. If the second cycle begins materially weaker, if the maintenance burden from the first cycle wasn't fully cleared, if consumable reserves are below the planned level for this point, if vehicle performance has degraded more than the maintenance work should have allowed. Day 100 identifies a trajectory problem. The site is degrading faster than the maintenance plan can restore it. That is the test. Not whether the crew is capable, not whether the hardware is impressive, whether the cycle holds. What the cycle reveals about the hardware is information no amount of pre-launch testing could produce. A vehicle battery that degrades at a certain rate per cycle under actual Mars traversal conditions tells the crew something they need to know before they plan the next cycle's distances. A life support component that requires slightly more frequent service under actual Mars operational tempo tells the crew to adjust the maintenance schedule before the shortfall becomes a problem. During the cycle, the crew also learns how to work at the pace this specific Mars mission actually requires, how long a traversal takes at this site, how much recovery time the crew genuinely needs after a high-tempo week, how many EVA hours per sol are sustainable before performance begins to degrade. Those aren't numbers the mission plan could provide with confidence. They have to be measured here with this crew under these conditions. By the end of the first cycle, somewhere around day 60 to 70, depending on how the tempo and recovery windows fell, the crew has operational knowledge that no Earth simulation provided. They know this site. They know how their specific hardware performs. They know their own capacities and limitations at this Mars location. A system can behave well for 1 month for reasons that don't last. Close monitoring, mild weather, first maintenance actions completed before significant wear had accumulated. A second cycle is less forgiving. It asks whether the procedures still work after the easy fixes have already been used and the hardware has begun to reveal its real habits. The repeat cycle protects the mission from false confidence. The first month shows competence. The second cycle begins to show durability. There's also a crew dimension to what the cycle tests that is different from the technical dimension. A mission's personnel plan assumes a certain pace of work. It assumes a certain distribution of tasks across the crew. Who maintains the life support stack, who leads the traversal planning, who handles communications scheduling, who performs the detailed maintenance on the surface vehicles. Those assignments were defined before launch, based on crew skills and training history. The first cycle either confirms that the planned assignments work under actual operational tempo, or it reveals that the workload distribution needs to be adjusted. Some crew members will find that their assigned responsibilities under Martian operational conditions take more time than training suggested, because the tasks are physically harder in a pressure suit, or because the specific hardware units on this mission require more attention than the qualification specs predicted, or simply because this person's work pace in this environment differs from what Earth training showed. Recognizing those mismatches early and redistributing tasks within the team, using the crew's combined skills more effectively rather than rigidly following a plan made on Earth, is part of how a first Mars crew takes care of itself. The second cycle can begin with better assignments than the first cycle was handed. That's an improvement the mission plan cannot make from Earth. It can only be made by the crew who lived through the first cycle. Now imagine the surface changing without drama. No alarm, no system failure, just a fine red powder settling quietly on everything the base owns, every panel, every sensor, every radiator, a little more each day, without ever announcing itself. This is Mars's most persistent environmental challenge, and in the spring of 2018, we got the clearest demonstration of what it can do. In the spring of 2018, orbital imaging of Mars began tracking a dust storm forming in the southern hemisphere. It started as a regional event, then it grew. Atmospheric scientists watching it saw the opacity index climb past values they had recorded only a handful of times in the history of Martian surface exploration. Within weeks, the storm had spread across most of the planet's visible disk. At its peak, it blocked more than 99% of direct sunlight in affected regions. The sky above Opportunity's location, a landscape the rover had been photographing for 14 years as a butterscotch haze, went dark enough that midday looked like deep twilight. Opportunity's solar panels could no longer generate sufficient current to maintain battery charge. The rover entered a low-power fault state. NASA sent commands for months. Engineers calculated the minimum power level that might allow the flight computer to respond if the batteries received any charge at all. They listened for any transmission. The rover never responded again. Its last data contact was June 10, 2018. 400 kilometers away, in Gale Crater, Curiosity sat through the same global storm. Its power source is a multi-mission radioisotope thermoelectric generator, producing electricity from the heat of radioactive decay in a plutonium fuel pellet. The storm that ended Opportunity was, for Curiosity, a mildly inconvenient science disruption. The rover couldn't use its mast-mounted cameras effectively because the light was too dim for useful imaging, and some external temperature sensors experienced unusual readings in the unusual atmospheric conditions. But curiosity kept operating. It took internal measurements of the dust event, collected atmospheric data, and waited quietly for the storm to end. In 2022, a smaller regional storm over InSight's location in Elysium Planitia reduced sunlight reaching InSight's solar panels below the level needed to maintain full operations. InSight entered safe mode, shedding non-critical loads. The lander survived the storm, but the incident added another data point to the documented record of solar-powered Mars surface assets being pushed into conservation or emergency mode by atmospheric events that are not unusual by Martian standards. The contrast between those outcomes, opportunity ending, curiosity continuing, InSight surviving by shedding load, is the sharpest operational demonstration available of why the power architecture choice for a crewed Mars base matters so deeply, and it's why the fission power decision matters so deeply. The storm history is the proof behind that decision. But the dust problem for a crewed base is about more than the storms. Regional dust storms affecting areas of tens of thousands of square kilometers happen several times per Martian year. Planet-encircling events are rarer but not exceptional. The instrumental record includes multiple examples. A first Mars base that treats dust storms as a low-probability contingency is a base whose risk model doesn't match the actual operational environment. And beyond the storms, there is something quieter and more persistent: the daily accumulation of dust on every external surface. It doesn't announce itself. It doesn't arrive as a crisis. It just settles, continuously. Solar supplementary panels, thermal rejection radiators, optical sensors, external cameras, all of them accumulating a thin coating that builds day after day without drama. Managing that accumulation requires scheduled work. Panel cleaning is an EVA task. Removing dust from thermal rejection surfaces is an EVA task. Inspecting and clearing dust from sensor ports and camera optics can sometimes be done with robotic assistance from surface vehicles, but often requires crew EVA. Each cleaning task consumes crew time, suit consumables, and the operational overhead of planning and executing EVA operations. The scheduling conflict is real. In the first 100 days, the maintenance load from system checkout, fault finding, and initial operational rhythm building already fills the EVA schedule. Adding unplanned cleaning tasks is a planning problem. The mission plan allocates EVA time. Every additional unplanned EVA competes with either planned productive work or planned maintenance. The first month's operational data on actual dust accumulation rates at the specific base site gives the crew the information they need to integrate dust management into the scheduled maintenance cycle, rather than treating it as an interruption. A cleaning EVA that happens on a planned interval is a known cost. A cleaning EVA that happens because something started failing is a disruption. Dust also changes the human schedule in a way that's hard to see from outside. It turns clean engineering margins into recurring labor. A panel that loses a few % of output every few sols doesn't fail dramatically. It simply asks for another cleaning task. A radiator that sheds heat slightly less efficiently doesn't announce a crisis. It increases pump duty, narrows thermal margin, and eventually needs inspection. Those requests arrive while everything else is also asking for time. The suits need service, the vehicles need charging, filters need replacement, communications windows have to be met, science plans have to be prepared, medical checks happen on schedule. The base that survives dust is not the one that ignores it. It is the one that makes dust work ordinary enough to fit into the week without swallowing the week. What the first month teaches the crew about dust at their specific site is something no orbital imaging could provide. Dust accumulation rates vary across the Martian surface. They depend on local wind patterns, the terrain features surrounding the base, the seasonal position in the Martian year, and the microtopography that channels or deflects air movement at ground level. The pre-mission dust models were derived from the best available atmospheric data for the candidate site region. The actual accumulation rate at the base is what the crew measures in the first month on their own hardware. If the actual rate is slower than modeled, the cleaning interval can be extended, freeing EVA time for other tasks without accepting a degraded panel output. If the actual rate is faster, the cleaning interval has to be moved forward, and the EVA schedule has to accommodate that shift without sacrificing other required work. Either result is useful. Either result is more accurate than the pre-mission estimate, and either result shapes the dust management schedule for the rest of the mission in a way that the original plan couldn't provide. There's a subtler version of the dust problem that the crew experiences rather than reads about. The way accumulation gradually changes the visual appearance of external hardware. A pressure suit left outside the airlock for an EVA gathers a fine coat of reddish material on any horizontal surface. Equipment staged on the habitat exterior changes color slowly from its manufactured finish towards something uniformly Martian. The surface vehicles, after traversal over unpaved regolith, return with their lower panels coated and their optical sensors requiring cleaning before the next traverse. The base begins to look like it belongs to its environment, which is not a problem in itself, but is a reminder that the environment is continuously asserting itself on every surface the base owns. A base that has managed dust in the first 100 days, not eliminated it, but managed it within the operational rhythm, has demonstrated something important. Mars's most persistent environmental challenge is a workable operational reality. The panels are at planned efficiency. The radiators are working at specification. The maintenance schedule accounts for the cleaning intervals that the first month confirmed are actually needed. That's the real day 100 condition for dust, not solved, managed. Let's stand at the far edge of the 100 days and look back, not for a celebration, for evidence, to see what has actually been proved and what hasn't. Stand in the dust on the surface of Mars at the end of day 100. The reactor is running. 1 kilometer back from the habitat cluster, the fission system has been converting nuclear decay heat into 30 kilowatts of electrical power. Through every Martian night, through the 2 regional dust apophis events in the first month, through the scheduled reactor inspection on Sol 72 that required the crew to manage on storage power for 6 hours while the maintenance team confirmed the reactor's health indicators. The storage performed as designed during that interval. The crew managed on battery power and maintained all critical loads. The reactor came back online. The power readings at the habitat end of the cable are within specification right now. They were within specification this morning. They were within specification through the Martian night. The habitat is pressurized at planned atmospheric conditions. Carbon dioxide partial pressure within the acceptable range for extended crew occupation. Oxygen partial pressure stable. The carbon dioxide scrubbing system completed its most recent filter replacement on Sol 93, and the replacement filter is performing within specification. The water loop completed its daily recovery cycle, and the total water inventory is within acceptable variance from the mission plan's day 100 baseline. The thermal control system cycled through last night's minimum, minus 68 Celsius at the surface outside, and the interior temperature held within the crew comfort range throughout. The surface vehicles are at operational charge. 3 traversal cycles occurred in the last 10 sols, each going out at full battery capacity and returning within the planned remaining charge margin. The supplementary solar panels were cleaned on Sol 94 and are producing at approximately 78% of their nominal output, 10 days of dust accumulation since the cleaning, which matches the accumulation rate the first month's data established. The fault log shows 18 entries across the full 100 days. 12 were closed on the same sol they were identified. 4 required a second inspection on the following sol before closure. 2 are on the scheduled maintenance list for the next cycle. Both assessed as manageable within their current service window, both with confirmed spare parts availability and defined service procedures. None of the 18 escalated to a state that required an unplanned mission-critical response. The crew's daily schedule in the last 30 days reflects a shift that happened around Sol 60. In the first month, more than half of available work hours were consumed by unplanned response, system verification checks that took longer than planned, fault investigation that displaced scheduled science evas, check-out activities extended past their allocated time because the actual hardware behavior required more investigation than the model predicted. By Sol 60, that ratio began to reverse. Planned productive work started consuming more than half the available work hours. By Sol 90, the crew was doing mostly planned work each Sol: geological survey traversals, sample collection, systematic surface mapping, science instrument operations, with maintenance occupying its scheduled slots rather than expanding into everything else. That is what Day 100 proves. It proves the base startup sequence works under these conditions, that the pre-crew cargo survived the pre-crew window in a state the crew could use, and that the landing was accurate enough to reach the pre-positioned assets from the first EVA. It proves the power system delivered continuous generation across 100 days, including a reactor maintenance event. It proves the habitat checkout produced a functional life support machine rather than a collection of underperforming systems, and that the maintenance load turned into a sustainable operational rhythm rather than a permanent emergency. It proves that all 5 preconditions, the pre-built site, the accurate landing, continuous power, integrated habitat and life support, and crew time shifting toward productive work, can be met at the same time. Each of those required different hardware to perform, different crew decisions to make, and different planning choices made years before launch to set up. All 5 being true at once at Day 100 is the bounded proof that a landing zone can become a base under the conditions of this mission. Day 100 does not prove that the Mars base is finished. The life support stack will continue requiring maintenance for the rest of the surface stay. The consumable reserves are past their 100-day mark, and the trajectory toward end of mission will need to be monitored. The dust management schedule continues. The next regional dust event will arrive at some unknown point. The surface vehicles need inspection before the next high-tempo traversal period begins. None of those ongoing requirements have been resolved. They are being managed. Day 100 does not prove that this architecture scales. The first Mars base has 1 reactor, 1 habitat, and 5 crew members. A future base with more crew, larger habitat volume, higher power demand, and more complex ISRU operations is a different engineering problem with different margins and different failure modes. The first base's successful 100 days establish that the initial configuration is viable. They do not demonstrate that every subsequent configuration will be. Day 100 does not prove that Mars is a safe environment to operate in. The next planet-encircling dust storm is somewhere in the future. The hardware degradation curve extends past Day 100 and will eventually reach components that no longer have the reserve to be repaired with available spares. The crew will complete their surface stay and leave. The site will enter another pre-crew window before the next mission arrives, and the hardware will endure another unattended period in the Martian environment. What Day 100 proves is first outpost operability at the bounded scale of this mission. The startup ladder works. It was designed before launch, built into cargo that left Earth before the crew committed to going, and proved across 100 days of maintenance and adaptation by a crew working through a real Martian environment. It works at this scale, with this hardware, in this season, at this specific location on Mars. The proof is bounded precisely because the conditions are specific: a different site with a different dust burden, a different power architecture with different storage margins, a different mission duration with different consumable requirements, or a different crew working under different operational tempo assumptions would require a new proof. Day 100 is not a general answer about Mars. It is a specific answer about this mission, at this site, to the question the mission was designed to answer. That specificity isn't a limitation of the proof, it is the point. The first Mars mission isn't supposed to prove that any Mars mission can succeed. It's supposed to prove that this mission can close the gap between a landing and a base within the first 100 days. If it can, the next mission has a foundation to build on. If it cannot, the next mission learns from what this one found. The fault log, the maintenance board, the power readings, the water inventory, the habitat atmospheric composition, the vehicle battery records, that accumulated operational record of 100 days. People and machines working together on a planet that doesn't make it easy, building something that had not existed before, is the actual evidence, not the footprint, not the moment of landing. The footprint is still in the dust nearby. Mars winds are slower than Earth winds and less erosive. The mark has not been erased, but around it the cable carries current. The habitat holds pressure. The maintenance board shows what comes next. The vehicles are charged. The crew has a plan for tomorrow. Before we leave Mars tonight, go back to the footprint. It's still there. The mark hasn't moved. The dust around it is undisturbed. But it's no longer the most important thing in the scene. The image most people carry when they think about this story is a single footprint in red dust. It's the right image for what a landing is. A boot-shaped mark pressed into a surface nobody has ever touched, by a crew that survived the entry, the descent and the touchdown. Real, earned, the product of decades of engineering and thousands of people's work. But a landing is an arrival, and the footprint captures the arrival, not the 100 days that determine whether the arrival becomes something more. Everything that makes the base possible was put in place before that footprint existed. The cargo that left Earth 26 months before crew departure is the actual foundation, not the landing vehicle that brought the people. The pre-landed habitat that survived a Martian winter before the crew ever launched. The fission power system that has been running since before anyone committed to going. The ascent vehicle sitting in the dust, its propellant tank slowly filling across the pre-crew window as the ISRU system pulled oxygen from the Martian atmosphere. That infrastructure is what the crew arrived to use. The landing vehicle brought the people. The pre-landed cargo made it possible for those people to stay. The cable that runs buried between the reactor and the habitat carries 30 kilowatts of electrical power, continuous, independent of weather and sunlight and dust. Without it, the habitat is a sealed shell in an environment that will eventually overcome it. With it, the habitat breathes. It stays warm through the Martian night. It charges the tools that maintain every other system. It keeps the crew alive in a place where staying alive requires continuous mechanical effort. The fault log that accumulated across 100 days is the clearest document the mission produced. 18 entries, each one a problem that was found, assessed, addressed, and closed or scheduled, not hidden, not deferred until they became crises. Worked through by a crew that chose to stay ahead of the failures rather than wait for them to force a response. The problems are not signs of a mission in trouble. They are signs of a mission that is looking carefully, finding what needs to be fixed, and fixing it with what it has. The maintenance board, with its upcoming service intervals and completed task records, is what an outpost looks like from the inside. Exploration is not yet the dominant daily activity, and science is not the heroic purpose filling every available hour. The disciplined record is the continuous background work of keeping a complex system operating in an environment that taxes every component, and then using the hours that remain after maintenance to do the science and exploration the mission was funded to accomplish. Day 100 is a proof point, not a celebration. The first bounded evidence that what was built before launch and what the crew has maintained since they landed adds up to something real, something that deserves a name different from camp. The base is not finished at day 100. The consumables will need managing for the rest of the mission. The dust will keep settling. The maintenance schedule will keep demanding attention. The crew will finish their surface stay and leave the site to another pre-crew window before the next mission arrives. The hardware will face another unattended period in the Martian environment, but the site will be there when they leave. And it will have proved, across 100 days, that it can function. That the systems around that first footprint can keep running without every morning becoming a recovery from the night before. The footprint is the moment. The base is everything that has to keep working around it. There's something worth noticing quietly about what the first Mars crew accomplished in those 100 days that won't appear in any headline. They didn't just keep themselves alive. They produced the first verified operational manual for human surface presence on another planet. Every adjusted procedure is a real procedure now, confirmed against the actual environment. Every updated maintenance interval is an interval that works in practice, not just in a terrestrial vacuum chamber. Every traversal route that was modified from the orbital plan is a route that someone actually walked at walking scale through real terrain. Those corrections matter enormously. Mission planners for the second Mars crew won't begin from models and assumptions. They'll begin from a verified operational baseline. The estimates that had to be used the first time can be replaced by measurements. The failure modes that appeared unexpectedly during the first 100 days will be accounted for in the design of the next mission's hardware. The spares quantities that ran low, or turned out to be more than enough, shape the cargo manifest that goes on the next launch window. The site that proved its operability provides a known infrastructure for the second crew to extend rather than rebuild. This is what a first mission produces that cannot be produced any other way. Not only the scientific samples, not only the survey data, not only the demonstration that humans can survive on Mars for 100 days, but the verified knowledge of what it actually takes. And when day 100 passes with the power steady and the habitat intact and the crew working from a routine, then Mars has, for the first time, a site that has earned a different name.